So this page is all looking at using trig functions to look at real-life examples and solve questions from those real-life examples. Now this first one is the easiest form of those examples because the equation is already given to you. We've got that the depth is negative 4.5 cos of 0.16 pi t plus 13.7. So the first thing we start to notice about real-life examples is the numbers don't always look nice. We have decimals here. We've got a b value that's 0.16 pi. So inside the equation it doesn't necessarily look as nice. But we can still use the same technique of d, a, and b, and then c to graph this. So I'm not going to get you to write this part down, but just to discuss some things here, when we look at that equation, that negative, that's going to reflect it over the x-axis. Our amplitude is going to be 4.5. Our period, well, our period is 2 pi divided by the b value, and when we do that and simplify it, we find out that our period is going to be 12.5. So we type this into our calculator. This, in particular, if you type this into your calculator, is a good place to make sure that if you have this fraction button that you use it. Because look, if I use the fraction button, 2 pi divided by 0.16 pi, I get 12.5. If you just type it in like most students do, 2 pi divided by 0.16 pi, look at how different your answer looks. What did I do wrong? I'd have to put brackets around the bottom. How easy is it to forget putting those brackets around the bottom? Super easy to forget. So that's why I would recommend that when we're typing that in, if you have that fraction button, you use that. If not, the idea is whenever you're dividing by more than one thing on the bottom of a fraction, you need to have those brackets there so you don't make that mistake. Okay, so that's our period. There's no horizontal shift on this one, and we do have a vertical shift up 13.7, and that's what our sinusoidal axis is going to be. So I'm just going to erase that for now because we're going to sketch this graph. All that we're going to write when we sketch this, we know that our d value is 13.7. Our amplitude is 4.5. Our b value tells us that our period, and we calculated that already, to be 12.5. How does this show up on our graph then? Well, I'm going to draw this line further down because I already know that my center line is up at 13.7. And if I choose that spacing to be 13.7, if I'm going to go up and down 4.5, I sort of have to estimate what would be an appropriate spacing for that. So if that's 13.7 and I go down 4.5, that'll take me down to 9.2. Up 4.5 will take me up to 18.2. So we label our d value, our sinusoidal axis. We use our amplitude to find our maximum and our minimum. Now our period is 12.5. Choose somewhere along your x-axis to mark 12.5 and split it into 4 equal sections. And label those 4 sections. And now, it's a cos graph. It's a negative cos graph. Where does a cos graph start? Normally, at a maximum. So where does a negative cos graph start? At a minimum. So it'll be down here. The next section will be to the middle, to the maximum, to the middle, and back down to the minimum. And I can draw this with a solid line right away because there is no c value. There's no horizontal shift. Now for part B says a bulk carrier needs at least 14.5 meters of water to dock safely. For how many hours per cycle can it dock safely? So for this, I'm going to get you to take out your graphing calculators because solving this is going to be easiest with our graphing calculators. First of all, if I mark 14.5, if I mark 14.5 on my y-axis, this is our level of our water. Oh, I should just add here that we have down here time in hours, and this is our depth in meters. So when we have a real-life example, we'd like to label things as clearly as possible and label what our axes are standing for. So according to this graph, in order for that bulk carrier to have, or that boat to be safe, the water needs to be deeper than 14.5 meters. So these are the two places on my graph where it's exactly 14.5. And anywhere where the depth is more than that, it's going to be safe. So it's going to be safe between here and here. And we need to figure out where that's going to be. So the first thing we're going to do is we're going to type in this equation into our calculator. So we're going to go to y equals, clear out things if you have anything else in there. And I'm going to type in negative 4.5 cos 0.16 pi x plus 13.7. So this is my equation. Now if I go and hit graph right away, I might not see this. Because what we want to do is we want to set up our window for a graphing calculator to show this part. In order to do that, on our graphing calculator, we need to go to the window button and we need to set things up so that we can see it. So along my x-axis, can you see that we go up to 12.5 in one period? So what I would like to do is I would like to see a little bit to the left. So I've got -2. That seems reasonable. I want a little bit of my negative numbers to make sure that I see my y-axis. I want to go a little bit past 12.5, so maybe I'll go up to 15. And what you choose is those numbers. If you went to 17 or you went to 20, it would be fine. It's just deciding how big along my x-axis I want to see. And this value right here where it says XSCL, that stands for X scale. That you can decide how many of these little ticky marks you want along the x-axis, how far apart they want to be. So for this one, since each of these are spaced equally at 3.125, I might even use that. So I get exactly the same as my graph. Along my y-axis, we went up to 18.2. So again, I might want a negative number just to make sure that I see my x-axis. But now I'm going to go up to 20 to make sure that I see my maximum. And my scale, since it's not going to work out perfectly, maybe I'll go by 5s. And now when we graph it, our graph shows up quite similar to the graph that we've created. So now, if we want to draw this horizontal line in here as well, That happens at 14.5. So when we go to our graphing calculator and we go to y equals, in y2, we can put 14.5 because that's the equation of a horizontal line. And now when we graph that, we get a straight line across. Your graphing calculator has some very powerful things built into it. So when you have two graphs, it can calculate where they intersect. All of the calculation things for graphs, well, most of them are found by pushing the second button, and then the trace button above it says calculate. And when you get to that, you can calculate different values, you can calculate maximum minimums. We want to do number 5, find out where things intersect. Now, when you want to find out where things intersect, it's going to ask you which curve you want first, which curve you want second, and then which you want to guess. For the most part, you just need to push enter 3 times, and it will find the closest intersection point. So where my cursor is right now, I think it's closest to this one. If I push enter once, cursor jumps to the second curve. Push enter again, it asks you to guess. Push enter again, and it finds it, and it's at 3.48. So it's telling us that this first one is at 3.48. If I want to find, so we just found that first intersection point. If I want to find that second intersection point, I go through that process again. Second, then calculate. Number 5, the intersection. But now I need to move my cursor over until I'm closer to the second one. You can probably do it quicker on yours. If I do it too quick, my calculator crashes. But now I think that cursor is closer to the second one. Push enter first, second curve, guess, push enter again. Sure enough, it found it at 9.02. That's the second intersection point. So, when is it safe? For how many hours? You could say from 3.48 to 9.02. So it is safe for, if we figure that out, 5.54 hours per cycle. So in certain areas where they do have tides that are changing quite drastically and they've got big ships coming in and out, depending on the dock, these would be important information. Now I'm also going to show you, because once you get into university, there will be some courses you're allowed to use a calculator, but you might not be able to use the graphing functions. So you'll be able to use a calculator, but not a graphing calculator. So if you're in a university course that is asking you to solve this same question, but you can't use a graphing calculator to put it into your graph to find those intersection points, which for the most part is quicker and easier, we can also solve this using the trigonometry that we already know. Now I'm not going to give you enough time to write this all down, and you don't have enough space to write it on this paper, but I'll show it to you and it'll be on the video so that if you want to look at it later, you can. So for right now, all I want you to do is to pay attention and to see if it makes sense. Okay? So we're still solving this question, and we're still thinking of this graph that we're looking for those 2 points where they intersect, because those are the places where the water is deeper than 14.5 meters. Well, in order to do that, the first thing that we realize is we need to find out where those two graphs intersect, and at that point we know that the depth needs to be 14.5. That's our y value. We can plug that into our equation for y, and then our equation looks like this. The only thing you don't know in this equation is t. So you use your algebra skills, your solving skills. How do I solve for something inside of cos? Well, I'm going to need my reference angles, I'm going to need to use my cast rule, and I'm going to need to find angles in different quadrants. So how does that work? Well, first of all, you would get cos by itself. So if I subtracted 13.7 on both sides, and then divided by negative 4.5, I would get cos by itself. Now, at this point, you might be thinking, this looks complicated because I've got extra stuff inside of cos. How am I used to solving cos equations? I'm used to cos equations that look, teachers always give us such nice numbers like negative 1/3 instead of 0.8 over negative 4.5. And they give us theta instead of a whole bunch of other stuff. Well, just because you have other things here doesn't need to make the question more difficult. Inevitably it does, because people get scared of bigger things and they find it harder. But in this case, we're going to solve this in the same way that we solve something like this. How do you solve something like this? You find your reference angle, you find it's going to be in quadrant 2 and quadrant 3, and solve for it there. So part of what we would do in a question like this is we say, well, let's make it easier. Wouldn't it be easier if I didn't have this and I had theta instead? These numbers actually I don't think are that much more difficult than 1/3. They're just decimals. But I don't think they're that much more difficult than using 1/3. But that inside looks like a problem. So that's what we do, is we temporarily let theta equal that whole inside thing. So that changes our question into something that we're more familiar with, and then we can solve. What would we do first? We'd do cos inverse to find our reference angle. Once we have our reference angle, what quadrants is it going to be in? There's going to be an answer in quadrant 2 and an answer in quadrant 3. And so we do pi minus our reference angle for quadrant 2 and pi plus our reference angle for quadrant 3. So now we have our two answers for theta. Theta is equal to 1.74 and theta is equal to 4.53. You would normally be done if it was just a cos theta question. But since theta was equal to 0.16 pi t, now we can substitute that back in. See what I'm doing? We temporarily made theta equal to this, and now that we're done solving for theta, we can change it back to what it was originally, because originally I wanted to solve for t. How would I solve for t in this equation? I divide both sides by 0.16 pi. Type this into your calculator, you get 3.48. The same thing we found with our intersection. Do the same thing with the other angle, and you get the 9.02. So this is how you would solve it if you were allowed to use a calculator, but not allowed to use a graphing calculator. They won't ask you a complicated question like this on your exam, but they will be expecting you to be able to do that once you enter university calculus courses and physics courses. So these are skills that you would need to have for those university courses. So I wanted to show you how you would do it without your calculator, and also show you how you could use your calculator to check, because it's kind of nice if you're doing an assignment, you want to see if you got it right. That's how you could use it to check. So our second example doesn't give us an equation, but it gives us enough information to draw the graph, and we've already learned that if we can draw a graph, we can find the equation by looking at DAB C. So first of all, we have a Ferris wheel with a radius of 15 meters. It rotates once every 20 seconds. So I'm going to draw a little Ferris wheel here. Fancy green seats on this Ferris wheel. Very nice. You can use this when you want to make it look like you're doing your math homework, but you'd rather be drawing. You can just spend time drawing the question out. You can put little people on your Ferris wheel, hands up in the air because they're living on the edge. So here we have our Ferris wheel, and I've drawn a picture off to the side so that when I go to draw my graph, I'm going to draw my graph right beside it, ground level there. You get on the Ferris wheel 1 meter above the ground. So we can mark that. If the radius of this Ferris wheel is 15 meters, how high above the ground will you get? You'll get all the way up the top where this guy is like having the time of his life, be 31 meters above the ground. What's the halfway point going to be? 16. Exactly 16. You can see the radius of 15, the radius is going to be the same as our amplitude. Now if it takes 20 seconds to rotate, can you see that if you're starting 1 meter above the ground, 20 seconds later is when you're going to be back to 1 meter above the ground? That's one whole period. When we're graphing something, we took our period and we divided it into 4 equal sections. Where are you going to be at 10 seconds? Way up there, having the time of your life. And then at 5 and 15 seconds is when you're going to be at your average. So we can put a dotted line here for our average. We can label that this is time, and our time is in seconds. This is our height, and our height is in meters. And we were able to draw the graph. Now that we've drawn our graph, we can write our equations. Our equations are going to be based on this. From here, what's our d value? What's our sinusoidal axis? 16. What's our amplitude? 15. Our b value, again, remember that your b value is always 2 pi over your period. So our b value here is going to be 2 pi divided by 20. And I actually would not reduce that. I know you can reduce it to pi over 10, but often in real life examples, when they make a real life equation, they'll leave it as 2 pi over 20, because when you leave it as 2 pi over 20, in the equation you're telling the person who's looking at the equation the period is 20. Because the period's always 2 pi, your b value is 2 pi over the period, so when you write it as 2 pi over 20, you're telling the person who's looking at it that the period is 20. Now your c value is going to change depending on whether you have a sine or cosine graph. So when we go to write this equation, we can make one with sine, one with cosine. Our amplitude is going to be 15 for both of them. One with sine, one with cos. Our b value is 2 pi over 20 for both of them. I'm going to leave space to write my c value after, and our d value is plus 16 for both of them. So our d, our a, and our b value are going to be the same for both. For a sine graph, where does a sine graph start? Sine graph starts in the middle going up, right? When does that happen? Here at 5. A shift of 5 to the right. So we could write x minus 5 for our sine graph. For a cosine graph, where does a cosine graph start? At a maximum. When does that happen? A shift of 10 to the right. Probably, and those are 2 examples of equations. There's more. Probably the most common one for this one would be a negative cos graph, because where does a negative cos graph start? At a bottom, and then there would be no shift. So you could write it just like that. we're going to end there, but what I'd like you to do before, in the last 5 minutes, is I want you to get this equation into your graphing calculator so that you see it just like that. You can choose any one of those 3 equations. They'll all be the same. And I want you to be able to graph that. So we'll finish up the rest of this paper in tomorrow's morning class.